Okay, the last item in chapter 10.1 is a significance test for the difference of proportions. We already did the confidence interval in the last video. This is a significance test. It's going to take a similar format. I would like you to start by reading book pages 630 through 637. Press pause while you do that, and then we'll get going. Okay, significance test about two proportions. The first thing that we need to talk about is, of course, the conditions. And as you can see, the conditions look very similar to what we've seen in the past. The data comes from two independent SRSs, or two groups in a random experiment. This we've seen before. This we've seen before. Once again, you might notice you have to check it for each proportion. So the first question we're going to do is in your alternative examples, and the question is who Instagrams. So let me pull that up. Stating a hypothesis and checking conditions. So it says the Pew Research Center recently selected a random sample of 269 18 to 29-year-olds and found out that 59% of them use InstaFace. A separate random sample of 401, so they actually sampled more 30 to 49-year-olds, found that 31% of them use InstaFace. Do these data give convincing evidence that a greater proportion of 18 to 29-year-olds use Instagram, InstaFace, Snap a Face, whatever, Snap a Tweet, than 30 to 49-year-olds at the alpha equals 0.05 significance level? State the appropriate hypotheses for performing a significance test. Well, duh. Yes, these people here use it more than old fogies like me. I mean, yes, there's evidence. So thank you, Captain Obvious. All right, here we go. Define both parameters of interest and check if the conditions for performing a test are true. So first of all, we're gonna make a hypothesis, and we'll have null hypotheses and alternative hypotheses, and if the P is low, H of O must go. We're gonna have all that stuff just like we have before. But the first one is conditions. So we have H of O, and the H of O, what I would start with is that there is no difference between the proportions. So my hypotheses would be the proportion of, I don't know, I'll just use P1, and the P young will be the youngsters, and then the P2 will be the old people. So P1 minus P2 is equal to 0. So my hypothesis is there is no difference. And my alternative hypothesis, the one I'm checking for, is that I think that, well, if I subtracted this proportion, which I think there are more of, minus this proportion, I'm guessing that P1 minus P2, well, that value should be more than 0. I should have a positive number there. And if I have a positive number there, well, you know, I can be assured that happens, that the younger people use it more than the older people. Where P1 is equal to proportion of 18 to 29 who use InstaFace, and P2 is equal to proportion of, and what is this? This one is 30 to 49 who use InstaFace, whatever, Snap a Tweet. I guess it doesn't really matter. But we have to check these proportions for the conditions. We have to check each one. So we have to check P1 set of conditions and a P2 set of conditions. So P1, is it an SRS? It tells us in the reading SRS. They're both SRSs. I have 269 of these people, so 269 right there. And I'm going to assume that's less than 10% of all in that age group. And how many did I have in the other one? I had 401. 401 is less than 10% of all in that age group. Those both check out. And then I have to do the large counts one, the with the percentage. So is 269 times the proportion that we found, which was 0.59, and then 269 times 1 minus 0.59, and then we have 401 times that proportion, which is 0.31, and then I have 401 times 1 minus 0.31, and again, all these have to be greater than 10. That's what we're looking for. Do we have more than 10? And they do, and these all check out. So we have our conditions met. That's the first thing. Second thing, now that we have conditions met, what does our interval look like? And this interval is interesting. It is big. There's some quirky things about it. It's again because we have difference of proportions. We have multiple pieces in here, but pieces that we have seen. And it's, you know, we have Z conditions again. That's something that we've seen before. And we're going to end up doing a Z test. We're going to end up doing a significance test to see if we can. And it's actually, again, a problem where it makes more sense when you actually see it in a problem format. But we have statistics minus parameter over the standard deviation. There is something quirky about this. Rather than P1 hat and P2 hat in these two spots, they actually use P hat. And the best explanation I could find of that was in the reading on 631 and 632. So if you want to know why these are P hats rather than P1 hat and P2 hat, you can go back and look at that reading on 631 and 632. They do a really good job of it, better than I can explain it, so you can look at that. But again, what we basically have is we have a statistic minus parameter over standard deviation. And our parameter right here is often 0. And that often 0, where that comes from, is it comes from our null hypotheses. Because what we said was, well, we don't think there is a difference. My H of O was that P1 minus P2 would be 0. There would not be a difference in that. So if we do find a difference and we subtract these out, what's going to happen is we're going to have a Z value that's kind of large, and we'll find the area under that curve with those two significant points. And if we find too big of a percentage, too big of a likelihood that this could happen by chance, we'll reject the null hypotheses and accept the alternative hypotheses. So I guess what I'm telling you here is this is going to be pretty standard, and the parameter value we're gonna state it as 0 because that's what we're testing. Is it more than 0? Is it less than 0? Where does it appear along that scale of around 0? And we'll be able to do some significance testing with that. So the problem that we're going to do, alternative examples, we'll do cash for quitters here in just a second. We'll do both of these. But we're going back to the Who Instagrams. And then after we do this one, we'll do the cash for quitters problem. And you guys will help me out with that. So a couple things. Let's find some values that we're going to use in our numbers here in our calculations. So I want P1, I want P2, and I want just the P value, the P hat value, the expected value of what I would get. And the P1 value, well, that was the expected 18 to 29-year-olds. So I'll help you get the P1 value. So it's 159 here out of 269. 159 out of 269. Press pause, see if you can find the P2 value. Okay, the P2 value was 124. 124 out of 401. And those decimals, I think, are what we found earlier, 0.59 and 0.31. 0.59 and 0.31. About 59% of the people in this specific sample, well, they used InstaFace, and 31% in this specific sample. But then what's the P hat that we're going to use? And the P hat is really the sum of these two values. So if I take these two values and I add them up, 159 plus 124. And I take their totals and I add them up. 269 plus 401. What I will find is I'll find this proportion for the entire population. In this sample, not population, in this specific sample, the expected p-hat, the expected proportion of people that would use InstaFace would be this. These are the specific age groups. This is the total population of our sample value, and you can run through that calculation. And I got 283 over 677, 283 over 677, and that's about 0.422. And that's probably not halfway in between, and the only reason I say that is because these sample sizes were different, but I do notice it's definitely in between, and I would expect that to be in between. So we have our values, and number one, it says, explain why the sample results give some evidence of the alternative hypotheses. Well, definitely some evidence, because this minus this, the younger age group minus the older age group, well, that's 0.59 minus 0.31, and that value is 0.28. And the fact that 0.28 is greater than or equal to 0, it tells me there's probably something going on here. This gives a little bit of evidence, but again, was it sampling variability that caused this? I mean, was the fact that maybe that sample size is smaller than that sample size that caused this? I don't know. Is this enough evidence? Is that a big enough gap with that sample that we can say, yeah, I think there's a difference? And I mean, this is kind of the same situation that we've been dealing with now for a while. So calculate the standardized test statistics, which will be the z-value, and then we'll do that. So what I would like you to do is I would like you to use the formula, and the formula is P1 minus P2 minus our 0 value, which we talked about earlier, and then that's all over the standard deviation. And the standard deviation, now remember, it's going to be p hats in there, not the p1 hat. So go p hat 1 minus p hat all over the number in the first one, the number of people. So that n1 value is the 269 value, and then I'm going to add to that p hat again, 1 minus p hat again, all over the n2 value. And we're going to get a critical value out of that. We're going to get a z value. Hit pause, plug numbers in, and see what you get out of that. Okay, what I got out of that was just a huge z value. A z value that, man, when I see one this big, 7.20, and I mean, just theoretically, if I have a mu of 0 and a standard deviation of 1, 2, 3, 4, 5, 6, oh my gosh, I'm way out here at like 7.2. I mean, what's the probability of that happening? It's minute. In fact, when I did this value, when I did this calculation, and I got 7.2, and then I went to my normal CDF, which is what you have to really do to find this area. I mean, what's the area out there in that tail? It's minute. So my area here that I'm going to do, the calculation I'm going to do, I'm going to go to normal CDF. And I'm hoping you're doing this with me on the calculator. And I'm going to put my upper of 7.2, my lower, lower 7.2, my upper at like 1,000. Of course, the mu and standard deviation, the mu 0, the standard deviation is 1. I mean, I got a value, I think when it did it, I got this weird scientific notation value in my calculator, but the essence of it is it's 0. I mean, it's so incredibly small that I got 0 there. So I'm here, and I'm on what conclusion would you make at the alpha equals 0.05 level Well, what I would get is, well, if the p-value is low, the alternative hypotheses must go. I'd write that in there. If the p is low, h of o must go. And I would write because p-value of really close to 0 is less than alpha of 0.05, we have convincing evidence that the proportion of 18 to 29-year-olds who use InstaFace is greater than 30 to 49-year-olds. And we can reject the null hypotheses that there is no difference, and we can accept the alternative hypotheses that the proportion of these people is greater. Okay, last thing we're going to do here, and then after we're done, you can do this, is a cash for quitters problem. And I'm going to help you guys set this up, and that's all I'm going to do. And then what you're going to do is you're going to finish it off, and then we'll be done with the confidence, not the confidence interval. We'll be done with the significance test part of this section. So it says, in an effort to reduce healthcare costs, a large company sponsored a study to help employees stop smoking. Half the subjects were randomly assigned to receive $1,000 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. By the way, Jesus didn't vape, neither should you. None of the 300 volunteers knew of the financial incentive when they first signed up. At the end of 1 year, 12% of those in the financial rewards had quit smoking, while 8% in the traditional group had quit smoking. The results of this study give convincing evidence that financial incentives help employees like these quit smoking. All right, so here we go. We're going to state, well, I'm going to have my H of O. And my H of O, I think that what would happen is if you provided $1,000 to quit smoking, more people would quit than wouldn't. I don't know. I don't know what happens. So I'm going to put the proportion who got, and I'm gonna go, yeah, hashtag $word. I'm gonna go P of $, minus P of none. Well, that would be my hypotheses, and my hypotheses, my null hypotheses would be that there is no difference, that I get a 0. But what my alternative hypotheses, what I think could possibly happen, that's H of O, what I think could possibly happen is that if I was to subtract these two, P of $ minus P of none, well, that one I think is going to be bigger than that one. So I think I should have a greater than 0 right there. That would be where I would start. Where P of 0 or P of $ is proportion who quit for the money, and P of none is equal to proportion who quit for nothing. We have a 2-sample Z interval, so I do know it's that. We have a sample for quitters and a sample for quitters with 1,000 and a sample for quitting with none. So it's a 2-sample Z interval. I do know that. And here's where I'm going to stop. What I would like you to do is I would like you to finish this. It takes a very similar form to the last one. It's almost the same problem. You can use the numbers. If you have questions over this, hopefully we can answer those in our next Zoom meeting. So why don't you guys finish this, and then what I will have is I will have a place for you to take pictures of your 10.1 extra examples and input that for a grade. All right, good luck.